I'd like to help you work through the specifics of a Chapter 9 homework problem regarding a simple gas turbine engine. This is one of the most basic analyses for a very prevalent engine that we observe throughout the world nowadays. So let's go ahead and get started. This is problem 938 in your textbook, and I'll read it and then we'll start looking at planning our work. Air enters the compressor of a simple gas turbine at P1 equals 14 pounds per square inch, PSI. T1 is 520 degrees R and a volumetric flow rate of 10,000 cubic feet per minute. Let's see, so I immediately recognize I've got English units to deal with. The isentropic efficiencies of the compressor and turbine are 83% and 87% respectively. The compressor pressure ratio is 14, and the temperature at the turbine inlet is 2,500 degrees R. On the basis of an air standard analysis, determine the thermal efficiency of the cycle and the net power developed in horsepower. Now, this is a very realistic problem. You can see with these compressor and turbine efficiencies given, they're very representative of a real problem. And also what's requested are also very reasonable performance measures that a mechanical engineer should be able to fairly quickly determine on his own or on her own without much guidance. So let's go ahead and start planning our work. Okay, so keywords. Simple gas turbine. When you see simple gas turbine, this little sketch should pop into your mind. This is a simple gas turbine, and this is a stationary gas turbine. It's one with an output shaft that's going to be running an electric generator. So this will be a stationary gas turbine. But also there's plenty of examples of simple gas turbines that are used to propel aircraft through the sky. And also some gas turbines used to propel ships through the water. And so when you see the word gas turbine, you should be thinking Brayton cycle model that's well covered in Chapter 9. It's a really important material. When you see the phrase air standard, that's your key to realize that you're going to be using air as an ideal gas with variable specific heat. Now, the translation of that is that you use table A22, in this case A22E for English units, to determine the air properties. For this problem, the compressor and turbine efficiencies are given. So that means that you're dealing with an irreversible but adiabatic process for both the compressor and the turbine. So reversible, not reversible and adiabatic. In other words, not isentropic, but irreversible and adiabatic. Okay, for this problem, you're given the volumetric flow rate, and you're going to need to find the mass flow rate. So really, that's going to be the place we get started, is given the volumetric flow rate, let's determine the mass flow rate in pounds per hour or pounds per second for this problem. Okay, air standard, a quick reminder, when you see the phrase air standard, a lot of folks get confused with the difference between air standard and cold air standard. So when you see air standard, recognize that your model is air as an ideal gas with variable specific heat, and the translation is I need to use table A22E for my properties, such as enthalpy H, such as PR, we'll talk about a little more later, VR if needed. So there's a background video that I offer. Let's see, I don't see how long it is. It looks like it might be about 45 minutes long, where I work out a couple of more worked out example problems in the Brayton calculations that I have in my playlist of air standard cycles on my YouTube channel. Okay, so as a reminder for ideal gases, Cp minus Cv equals R for all ideal gases. For our air standard model, H2 minus H1 is the integral of Cp dt. Now, Cp is a variable, so that means that we cannot use Cp delta T. That would be only for constant specific heat. So for our properties, we're going to be going to table A22 to determine things like enthalpy, such as H2 and H1, separately. Another very powerful fundamental for ideal gases with variable specific heat and undergoing an isentropic reversible adiabatic process, we're going to use this first fundamental a lot in this solution. PR2 over PR1 equals P2 over P1. And the reason is that P2 over P1 is given in the problem statement. Do you remember P1 is given as 14 PSI? And also what was given was the pressure ratio, P2 over P1 is 14. So we're going to use this fundamental for isentropic processes a lot. Okay, let's start with a sketch and remind ourselves what we've got. So here's like an image of what a simple gas turbine looks like. Okay, 1 to 2, the compressor process. Here's our sketch. 2 to 3, the combustion chamber process that we're modeling as heat addition, the heat exchanger process where we're adding heat to the compressor outlet. We're going into the turbine. Here's process 3 to 4, the turbine process 3 to 4. Notice how the turbine is mechanically linked. Here's the shaft mechanically linked to drive the compressor, just as shown as our basic sketch here. But the turbine makes more power than the compressor requires. So there's an amount of net power that is delivered outside the control surface. So I hope that this gives you a feel for what a picture of a simple gas turbine looks like, coupled with what your homework sketch will look like in your analysis, labels 1, 2, 3, 4, 1. And look, over here in my slide, I've drawn a piston and cylinder. I put a big X through it. And a lot of students, when they get into chapter 9, they first start talking about Otto cycles and diesel cycles that are pistons and cylinders, internal combustion engines. Okay, and then we move on very quickly to the Brayton cycle, which is not a piston and cylinder. It is not a closed system model. Do you see here that just by looking at the image, we're looking at 4 open system components operating as steady state, steady flow components. Okay, 1 inlet, 1 outlet for each of those. Okay, and they're all put together in terms of a system operating in a cycle at a certain rate. And so notice here in my sketch, look how I don't have W net like we did for the Otto and diesel cycles. I've got W dot net. That's net power, not net work. These are some really important and fundamental things that you need to have a good feel for, rather than just applying formulas blindly. When you have a Brayton cycle, a basic gas turbine with open systems, where you really want to start is with a temperature entropy diagram, not a pressure specific volume diagram. So it's important that we see how our sketch, our TS diagram sketch looks for our specific problem. Here's our equipment sketch. Now, TS diagram 1 to 2. Well, if our compressor were reversible and adiabatic, it would be isentropic. And so on this TS diagram, we would show it as 1 to 2I, 1 to 2I. Look at that, a vertical line, constant entropy. Okay, the book calls this 2S. I call it 2I in my world. Now we know we're given in the problem that the compressor has a certain efficiency. So it's adiabatic, but it is irreversible. So that says that the entropy S2 is going to be a bigger value than S2I. So we immediately draw along a line of constant pressure here. The book says state 2. I call it 2A for 2 actual. That's the way I was taught. And that helps me keep track more straight, what's the difference between 2A, 2 actual, and state 2I, 2 isentropic? That helps me keep straight in solving the problem. I've shown 1 to 2A as a dashed line. You always show an irreversible process as a dashed line on a TS and a PV diagram. Okay, so there's our compressor process, 1 to 2. Then we add heat. We add heat to the air at constant pressure. I've got a little image coming up to show you what a real honest-to-goodness combustion chamber looks like. But right now, let's just say that this combustion chamber, the heat addition process, is a constant pressure process. And there's what a constant pressure line, an isobar, looks like on a TS diagram. Maybe should be a little more curved up, but let's just say this is going to be okay. Constant pressure line, P2 equals P3. Okay, then we get, I remember that our problem statement said T3 was given. The inlet state to the turbine was given, T3, that's given. Now, if our turbine were reversible and adiabatic, it would be a vertical line going from 3 to 4i, constant entropy. Now, we know it's not, but we draw in the isentropic turbine process, 3 to 4i, a solid line, that's reversible and adiabatic. But we're given turbine efficiency, so state 4 is going to be to the right, increased entropy from 4i. And so I'm showing it as 4a. Dash line process 3 to 4a, that's the actual turbine process, okay? And then a heat rejection process 4a to I that we really don't mess with. We don't need to mess with that process. We've got enough to answer our questions. What's the thermal efficiency? And let's see, what is the net output power? Simply by analyzing states process 1 to 2, 2 to 3, and then 3 to 4. What I'd like to do is give you a little visualization of little w actual. So remember what little w is. Little w is w dot divided by m dot. A little more about that in a second. But you can visualize with your experience so far sort of a measure of the work, w dot over m dot, on a TS diagram by remembering that for an ideal gas, the temperature and the enthalpy are either proportional or nearly proportional. And so enthalpy is a function of temperature only for any ideal gas. So do you see that if you look at this vertical distance, 3 to 4a, that's sort of a visualization of what's really being produced by the turbine, w dot over m dot. And this vertical distance from 1 to 2a, that's a visualization of the amount of work, w dot over m dot, that the compressor requires. Okay, so think of, as you're drawing and looking at your TS diagrams for the Brayton cycle, that has been a very handy visualization for me. And now, I didn't come up with this on my own. It was Dr. Walter O'Brien, when I was taking graduate level thermo in his class. He's the gentleman that explained this to me so well, where the light bulb finally went on. And it was Dr. O'Brien that really helped me get a good understanding of sort of the value of a TS diagram and a way to visualize work for a simple gas turbine cycle. The basics of a basic Brayton cycle. Here's our schematic diagram of any system operating in a cycle at a certain rate. Notice the dots, certain rate. And so we've got 4 components that comprise 4 open systems. We put them all together and they make a cycle operating at a steady rate. Okay, so remember the thermal efficiency for the Brayton cycle is the energy sought over the energy that costs. And just like all the other power cycles, what are we seeking to do? We're seeking to make net power, w dot over m dot, so that's just a little w. And what does it cost us? Well, we've got to buy fuel to run our gas turbine engine. So that's going to be similar to the heat added, Q dot H over m dot is going to be little qh. So the volumetric flow rate. Okay, volumetric flow rate is given 10,000 cubic feet per minute. This is a great place to start. Okay, and so we simply remember from weeks ago, m dot is equal to rho AV, or rho AV. That is the volumetric flow rate, A times V, volumetric flow rate, divided by little v. So either of those you've committed to memory, and that's where you go. And you say, now how am I going to get m dot? I'm given A times V, volumetric flow rate. If I can find the specific volume, I've got the mass flow rate, and I have enough information to determine at state one, the density, rho 1, is P1 over RT1, or little v1 is equal to RT1 over P1. And so we solve for m dot. Let's see. We're in English units, so we need R for air. And if we haven't committed that to memory, remember that R for air is R bar over the molecular weight of air. We definitely remember that R bar is 1,545 foot-pounds force per pound mole degree R, and the molecular weight of air is 28.97 pounds mass per pound mole, to give us an R for air of about 53.33 or 53.34 foot-pounds force per pound mass degree R. Okay, let's see. Where do I start on the analysis? I've studied my given information. I study my information. I see that I've got P1 and T1 given. I know I need mass flow rate, so I'm going to start at state one, and then I will just work my way around the cycle, because I need to, what do I need to determine? I need to determine the work required by the compressor. I need to determine the heat added, QH. I need to determine the work produced by the turbine. That will give me the net work, and that'll give me the thermal efficiency. And the net work times the mass flow rate will give me the net power. Okay, I was wondering where this slide was. I should have put it up a little sooner, but here it is. It's a friendly reminder. Let me see if I can get there's Snoopy. Some little friendly advice, just a little memory refresher. The textbook throughout chapter 9 uses little q and little w. And I want to remind folks, for our basic Brayton cycle, what does that mean? What do little q and little w mean for a basic Brayton cycle? Well, little q is q dot, the rate of heat transfer in, divided by the mass flow rate, m dot. Similarly, the work out, or W net, is W dot, the output power, divided by m dot. Okay, and gosh, for my slide, I have put in SI units. Okay, well, let's see what's that going to be for. What's that going to be for English units? Well, W dot out, we're going to need to figure out BTUs per second, for example. BTUs per second would be our output power units. M dot, that would be pounds mass per second. Okay, BTUs per second divided by pounds per second, that'll be little w out, little q in, will be BTUs per pound mass. So sorry about putting in the SI units in an English system, but that's your friendly reminder for what little q in and little w out is all about for the Brayton cycle. Okay, we're getting close to putting pencil to paper, but let's plan our work for our different processes. Process 1 to 2. The first thing we're going to do is study the isentropic process 1 to 2i. Once we can find the work, W dot over M dot, for the compressor 1 to 2, then we can solve for the actual work needed by the compressor. So studying the isentropic process first, we've got, for any ideal gas with variable specific heat and an isentropic process, reversible adiabatic, P2 over P1, known, equals PR2 over PR1. We will look up PR1 because it's a function of T1. We'll go to our table A22. Since P2 and P1 are known, we'll solve for PR2. That's going to give us an ability to go in our table to back calculate or interpolate for T2i and H2I. That's what we need. So that's, oh, and of course, here's the visualization of what you're studying. You're studying the reversible adiabatic version of this compressor section in your gas turbine. Now, once you've gotten H2I, then you can use the first law, determine W isentropic for the compressor. W isentropic for the compressor. That's going to be the first law. Let's see. For the isentropic compressor, for an adiabatic compressor, Qin is 0. So Qin, 0, minus W out equals H2I minus H1. Okay. And so therefore, Wi for the compressor is going to be H1 minus H2I. I just flip the minus sign. And so that's going to be a negative number. You see that visually, do you see that H2I is a bigger number than H1? So Wi of the compressor is going to be a negative number. Okay. And there you go. We're still working on the compressor. So we just studied the isentropic compressor, and you're given compressor efficiency. And I'm going to suggest that without going to a formula sheet, you should be able to know how to determine the actual work of a compressor if you have the isentropic work and the compressor efficiency. Just figure it out, okay? Compressor efficiency, what would you expect to be more? Would you expect it to take more power to drive an actual compressor compared to a reversible adiabatic compressor? I'd expect it to take more power to drive an actual compressor. So I put down, there's my definition of compressor efficiency without going to a formula sheet, because compressor efficiency has got to be less than 100%. So W actual is simply going to be the isentropic compressor efficient, isentropic work, W dot over M dot, divided by compressor efficiency. All right. So now you're getting somewhere because you need W net. You're halfway to W net. Looking ahead to the combustion chamber process, do you see that you're going to need H2A? Do you see you're going to need H2 actual going into the combustion chamber to calculate how much heat is added? You're planning ahead a little bit. So I need to figure out what H2A is. Well, what I'll do is I'll write the first law for process 1 to 2A. Process 1 to 2A, first law. Let's see. It's an adiabatic compressor. Qin is 0. So let's see. Qin, that's 0, minus W actual of the compressor equals H2A minus H1. So we'll solve for H2 actual. And here it is. H2 actual is simply H1 minus W actual of the compressor. Remember, it was a negative number. So sure enough, H2A is going to be a bigger number than H1. Now, this isn't a formula. This isn't something you just sort of write down for the textbook. It's something you derive from the first law. Okay, let's move on to determining the heat added in the combustion chamber model. Okay, here, process 2 to 3. Here is I mentioned, got to move my picture here. I mentioned earlier on that the combustion chamber process is a constant pressure process. And maybe in class, instructor said, it's a constant pressure process. Don't worry about it. It's constant pressure. Well, let me try to give you here is a cutaway image of what a gas turbine combustion chamber process looks like. It's just like a canister, okay, with some internals to get a good steady flame and a good stable flame. But here's process 2 to 3. It's flowing through a canister. Here's state 2, and combustion happens in this chamber, state 3. So basically, with combustion just flowing through a chamber, that's a pretty good, a constant pressure process is a good model for this. And so I'm hoping to sort of illustrate to you that process 2A to 3 occurs at constant pressure. Okay, well, I got off track a little bit. I talked about constant pressure. What are we trying to do? We're trying to find QH. Wow, that's going to be pretty easy. Do you see this canister? Is the canister lifting a weight? No. Is there a rotating shaft coming out of this canister? No, no. So the work out for process 2 to 3 is 0, no work out. So QH, first law, QH minus W out, 0, equals H3 minus H2A. Let's see, I just found H2A. H3 is easy to look up because T3 is given. I'll look up H3 in table A 22, okay, and straight plug and chug on QH. Now we're sort of coming down the home stretch on planning. We're going to analyze turbine process 3 to 4I. 3 to 4I. Here's what we're talking about on our basic gas turbine. There's the turbine section of the gas turbine. All right. We're going to study 3 to 4I, the reversible adiabatic process, so we can say that this fundamental P4 over P3 equals PR4 over PR3. We're going to look up PR3 because T3 is given. We'll just look that up. It's a number. Now, let's see. P3 equals P2, and P4 equals P1. So P3 divided by P4 is simply 14. Okay. So all that's known. So it's simple for us to solve for PR4. Once we have PR4, we're gonna go to our table, A22. We're going to back calculate or interpolate H4 isentropic and T4 isentropic. Not bad. Well, so what? Well, so what is, now we can write the first law for process 3 to 4A. Let's see, Qn, 0, it's adiabatic, minus W isentropic of the turbine equals H4I minus H3. We solve for W isentropic of the turbine, H3 minus H4I. Boom, we've got little w isentropic of the turbine. Now, a little easier, we've got turbine efficiency. We know it's got to be less than 100%. Our good common sense says, let's see, how much power would we get out of an actual turbine compared to a turbine that were reversible and adiabatic? A little less, get a little less power out. So turbine efficiency, easy to figure out, W actual over W isentropic. And so now immediately we simply multiply our isentropic work, W dot over M dot, by turbine efficiency to get W actual, W dot over M dot. Well, then we've got W net. Woo, great. We just a couple of minutes ago determined QH. We've got the thermal efficiency. And let's see, little W net times M dot, which we found as our very first step. We multiply those two together to get the net output power. Okay, I just said that, didn't I? Oh, and one reminder is, I think the problem said, what's the net output power in horsepower? So what we're going to look up this conversion factor in your textbook. 1 horsepower is 2,545 BTUs per hour. So that is going to be a conversion that you're going to write down on your solution. In fact, that's something that good mechanical engineers have in their heads. 2,545 BTUs per hour equals 1 horsepower. Just a little reminder, you say, wow, you're dragging me through all of these things. We've got some formulas in the book for a Brayton cycle that I could bang this out a little faster. And that could be true, but I do want to remind you that if you really need to understand these fundamentals as you go through your homework solutions to prepare yourselves for quizzes and tests and for being a practicing engineer. So your best formula sheet is your head. So the more you can simplify things, keep the things you must memorize to a minimum, that's going to benefit you as you go into quizzes and tests, rather than depending on formulas that you blindly write down on a formula sheet. Okay, so now we're ready to start putting pencil to paper and getting some numbers. And so let's see, the first thing I'm going to do is determine the mass flow rate starting at state 1. So let's see, I need V1, don't I? V1, specific volume. So I'll write down, let's see, P1, 14 pounds per square inch. Now, looking ahead in our ideal gas law, remember, we've got to keep our units straight, and square inches don't appear in R. So I immediately transform pounds per square inch into pounds per square foot. That's something that a lot of students overlook. So I multiply 14 by 144 to get 2,016 pounds force per square foot pressure at state 1. T1 is already given in absolute temperature, 520. Got it. R bar, 1545. Molecular weight, 28.97. Okay, so R bar over the molecular weight is R for air, and we've got 53.33 foot-pounds force per pound mass degree R. Notice the feet there, okay. And then also, let's see, what else did I do? I divided this number 53.33 by 778 to get another expression for R of BTUs per pound mass degree R here. Okay. But let's determine V. What's the specific volume V1? V is RT over P. That's the ideal gas law. Should have that in your head, of course. So V1, so I used P1 in pounds force per square foot to get V1 is 13.76 cubic feet per pound. So I take the reciprocal of that to get rho 1. Rho 1 is 0.0727 pounds mass per cubic foot. Okay? And so let's see. I use m dot equals rho AV. Okay. And so I've got my input number, 10,000 cubic feet per minute, 10,000 cubic feet per minute. There's my input value in yellow, 10,000. And so let's see, m dot is rho 0.0727 times AV, or 726.95. Okay, pounds per minute. And I've made in my notes here, I said, oh, don't forget, you've got pounds per minute, not pounds per second. And so that's going to be, I got to remember what my units are for m dot. All right. When I'm studying a gas turbine cycle, the next thing I do is write down the rest of my given information right here and now. So P2 over P1 is 14 given. T3, the turbine inlet temperature, 2,500 degrees R, absolute temperature. Compressor efficiency, 83%. Turbine efficiency, 87%. Those are given. Okay. So I'm on my way to solving. The next thing I do is I'm going to just start working around the cycle. Isentropic compressor process 1 to 2I. So for an isentropic process, P2 over P1, that's going to be 14, equals PR2, don't know it, divided by PR1, need to find it. Okay, so here we go. Table A22E, at 520 degrees R, I'm going to look PR 1.2147. And also, based on my planning, I've got to write down H1 because I'll be using the first law, 124.27. So here they are. Wrote them down. Here's my pressure ratio from above that I already wrote down. So I'm going to solve for PR2. PR1 times P2 over P1, 17.006. Now, okay, that's great. I've got PR. What do I need to do? Well, I need to find H2I, and I'm going to find T2I as well. I don't have to find T2I, but I've definitely got to find H2I. So let's see. I'm going to go back to my table A22, and I've got to go shopping. I've got to shopping for a PR value of 17 and change. So I'm going to shop. I'm going to keep moving my picture around. Here we go. Over on the right side of table A22, here's a PR of 16.3 and 18.6. I'm in between those. So I'm going to set myself up an interpolation table to solve for H2I. So let's see. Here's my PR values that I got off the table. Here's my PR value, 17.006. The H values I got off the table, so I'll linearly interpolate to get H2I is 264 BTUs per pound mass. Okay, so I've got H2I, and just in my solution, I wrote down T2I as well. So I just found this, okay. And H1, I looked up already, so I wrote it down. Here's H1, 124. I'm going to apply the first law for the isentropic compressor. WI, okay, I think we showed in our planning. Let's see, Qn, 0 minus Wi equals H2I minus H1. So I've got to flip the sign. So this is the statement of the first law. W isentropic of the compressor is negative 139.8 BTUs per pound. That makes sense. It's a negative number. Compressor efficiency, I already wrote down. So instead of using a formula, I think, now, is WA compressor going to be a bigger negative number than that? Yes, it is. So in my work, I said, well, shoot, the only way to make it bigger is to divide this number by a fraction, 0.83. And so I've got isentropic compressor work divided by compressor efficiency is the actual compressor work, W dot over M dot, negative 168.5 BTUs per pound. Okay, the next thing I got to do. So, okay, I got W actual. That's going to help me for my net work. But now I'm moving ahead to the combustion chamber, the heat addition process. I need to write the first law for process 1 to 2A. 1 to 2A. Let's see. Qn, 0 minus W of the compressor actual equals H2A minus H1. So therefore, solve for, so let's see. H2A is going to be H1 minus work actual. Okay, so it's going to be a bigger number than H1, 292.76. Okay, there we go. So, gosh, here's my statement of the first law. Okay, solving for H2A, I move that over there, move that over there. H2A is H1 minus W actual. Okay, so H2A, we've got it. We've got the inlet to the combustion chamber, inlet to the heat addition process. Next thing I got to do is find out the enthalpy leaving the heat addition process model, combustion chamber. I'm given 2,500 degrees R. So I'll go back to table A22, look up H 645.78, okay? And also looking ahead, I'm going to write down PR3 because I'm looking ahead to my next task, the turbine process. So I'm going to write down that PR3 is 435.7. I made a little green box here, made a note. I got to write that down. PR3, 435.7. Okay, let's see. So H3, 645.78. So let's see, what am I looking for? I'm looking for QH, little QH added, first law for the heat addition process, H3 minus H2A, because there's no work done in the heat addition process, constant pressure. QH is 353 BTUs per pound mass. Okay, what's next? The isentropic turbine process. Isentropic turbine process. Okay, so let's see, what do I remember from there? Well, P4 over P3 equals PR4 over PR3. Got it. That's the isentropic relationship for ideal gas, variable specific heat, isentropic process. So let's see, PR3, I just wrote down. P4 over P3, that's known. P4 over P3 is 1 over 14. Okay. So I can solve for PR4. So here we go. Let's see. There's P4 over P3 is 1 over 14, 107. Okay. PR3 just looked up, 435.7. So PR4 is 31.21. So what? Well, I got to go shopping. At least that helps me to go shopping in my table for H, for H4 isentropic. Let's see. So here we go. I'm in between these two numbers, 31.121. In between these two numbers, I need to interpolate for H. I'll also go ahead and find T4 isentropic. Okay, so here it is. Here's my interpolation table. You see where I got these numbers from my table A22. So linear interpolation, I've got H4 isentropic is 313.36. T4 is 1286 degrees K. Didn't need to find it, but just out of interest, I found it. And H3, I already have. I've looked that up. So I've got it. Do you see? I've got my two enthalpy values. So I can write the first law for the isentropic turbine. Okay. Well, let's see, no heat transfer. So the isentropic turbine work, Wi is H3 minus H4I. Statement of the first law. 332.42 BTUs per pound. That's the isentropic turbine work. Right? Well, now I remember turbine efficiency. Should be like child's play now. Here's our isentropic turbine work, 87% turbine efficiency. Should I expect my turbine work actual to be bigger or smaller than isentropic? Of course, smaller. So I'm going to multiply my isentropic turbine work by the efficiency to get a smaller number, 289 BTUs per pound. Just good common sense, figuring things out rather than using a formula sheet. Okay, so I've got W actual a turbine. Wow, looking ahead, now I think I've got W net. Okay, let's see. Whoops, here it is. Yes, I've got enough to determine the W net and the thermal efficiency of the cycle now. So here's my two work numbers, W dot over M dot, negative 168.5 BTUs per pound for the actual compressor, 289.21 for the actual turbine, BTUs per pound. Add them up, 120 BTUs per pound net work. QH, 353.02 BTUs per pound. Look at these units are consistent. So with consistent units, I can calculate the thermal efficiency, W net over QH, 34.2% thermal efficiency. Wow, I'm almost done. The net output power. Okay, so I've got W net and BTUs per pound. I remembered my M dot units, 726 pounds per minute. Okay. Now, I've got a multiple. Now, so M dot, what I'm going to do, I'm looking ahead to my conversion factor. Look at, I've got BTUs per hour equals 1 horsepower. 2545 BTUs per hour equals 1 horsepower. 2545. Okay, so I kind of need to get my M dot in pounds per hour. How would I get M dot in pounds per hour if I've got pounds per minute? I simply multiply by 60 because there's 60 minutes in an hour. So I'm going to get a lot more mass in 1 hour, 60 times more than I get in a minute. So I multiplied 726.95 by 60 to get 43,617 pounds per hour. So now I've got W dot net, M dot times little w net. Look at my units. So I'm going to keep my units going. A huge number of BTUs per hour. Gosh, that's 5.27 million BTUs per hour. 5.27 times 10 to the 6 BTUs per hour. Divide by 2545 to get my unit straight in horsepower. And so I've got 2,069 net horsepower being delivered to something else outside the system operating in a cycle. Okay. And that something else could be a propeller of an aircraft engine, or it could be an electric generator on the ground. So those are two practical examples of simple gas turbine cycles. And I've shown a little icon of you. Here's your head, and I've pointed to it. And so it's my hope that you're strongly considering trying to get these fundamentals into your head rather than depending on a formula sheet or fishing formulas out of a textbook to try to get things to work out on your homework problem. This is your best formula sheet. And so one last thought. Do you have any interest in real-world equipment like these? This is a gas turbine electric power plant. Very common because the fuel is nowadays is natural gas to drive this gas turbine driving a power plant. Here's a propeller-driven aircraft, and the propellers are driven by a gas turbine. There's a jet engine, a jet aircraft. It's a jet fighter craft. Okay, those are turbojet engines, and this is a high-speed, small, fast attack destroyer type vessel that is where the power plant is a gas turbine that drives. It's basically a large-scale pump, so it would be a lot like a jet propulsion, a water jet propulsion, high-speed, low-draft ship. So if you have any kind of interest in perhaps working on these types of pieces of equipment as a career, getting really good at analyzing the basic Brayton cycle engine is going to really pay off for you. It's going to give you a step ahead of many others who do not have that capability. So let me encourage you to do your Brayton cycle analysis homeworks, to prepare yourselves to work well on quizzes and tests, and also prepare yourselves to be a step ahead when you get out into the work world. So that's it. That's my little demo of a worked out, basic, quote unquote, simple Brayton gas turbine engine cycle.